Recently, I've been wanting to better understand flash attention, specifically the flash attention varlen function, the variable length interface. And I've also wanted to better understand modern BERT's sequence packing implementation. And I've also started very recently, like in the past week or so, using Gemini 2.5 Pro. And so I thought that as a first kind of collaboration with AI, with Gemini, I thought that I would perform a deep dive on flash attention variable length, so flash attention for sequence packing, and do that in a way where I could come out of it with the ability to present a thorough blog post, video presentation with visuals. And so this is kind of my first project with Gemini 2.5 Pro. After using Claude for about a year on a daily basis, I'm trying out Gemini 2.5 Pro. So I'm very excited, and so far I'm very, very pleased with how it communicates. So I gave it the flash attention repository, and then I gave it my goals of what I was trying to achieve. And after a couple of back and forth messages, it came up with this timeline for understanding the flash attention varlen func implementation to a degree where I could explain it in a presentation. So there's three phases. Phase one is Python layer and sequence packing concepts. So tasks include understanding the variable length functions Python call stack, the role of cumulative sequence lengths, max sequence length, and torch autograd.function. And the time it estimates for this is 1 to 2 weeks with approximately 15 or to 30 hours. This is already, I think, a underestimate given how in this video I'm going to walk through just the very tip of the iceberg of the flash attention varlen func Python call stack. I literally couldn't get past the Docstring at this point. So this is an exploration of what I've learned in terms of understanding the flash attention varlen func Docstring. And that's almost taken up, I don't know, a third or half of the 15-hour lower estimate. So phase two is the core CUDA kernel deep dive. This is 6 to 12 weeks. This is going to be very difficult for me because I'm not very familiar with C++ and CUDA. And so the task is going to be starting out with studying the flash attention research papers, which I can do. That's something I'm good at. Analyze the C++ CUDA dispatcher code, something that's very intimidating to me. Dissect the core CUDA kernels for variable length forward and backward passes. Obviously very critical, very important. Sounds like that's where the meat of this is, and I think that's going to be the hardest thing to understand. And the number of hours is 125 to 240 hours, so big chunk of work. And then phase three is content creation, which is going to be a video and a blog post. And this is going to take about 2 to 3 weeks, approximately 30 to 50 hours. So the overall CUDA path is going to take about 2.5 to 4.5 months with up to 320 hours of work. So these are obviously very rough estimates. Gemini 2.5 Pro doesn't have a ton of context in terms of my pace and how I work, so it's just going off of my context that I provided in the prompt. So this could be, 3 times this amount. It might take me a year to get through this. So this is the motivation of this blog post / video. And the name of this video is HuggingFace's default KV cache and the flash attention varlen func Docstring. So it's a bit of a peculiar name, but I started out by reading the flash attention varlen func Docstring. And in the Docstring, they have this segment where they say if causal equals true, the causal mask is aligned to the bottom right corner of the attention matrix. For example, if the query sequence length is 2 and the key sequence length is 5, the causal mask, where 1 equals keep and 0 equals masked out, is as follows. So a 2 by 5 matrix. If you flip that, and the query sequence length is 5 and the key sequence length is 2, the causal mask is a 5 by 2 with these values masked out and these values we're going to keep. If the row of the mask is all 0, the output will be 0. So for background, I've never dealt with attention matrices where the Q and K sequence lengths are different. Everything I've studied so far, it's always a square matrix, when we're looking at the diagrams or when I'm looking through code or when I'm stepping through the causal mask to try to understand it. In all cases, I'm used to a square matrix, and that makes, intuitive sense to me. So this was right off the bat very unfamiliar for me. And so I started a conversation with Gemini, and through that conversation, because I'm using Hugging Face transformers as kind of my interface with flash attention at this point, we came across the topic of KV cache. And so I went into a little bit of a deep dive in terms of what the KV cache involves. So that's, I think, enough of a preface. I do kind of want to jump in and just kind of walk through the code, but just for reference, this is the motivation. This is hopefully one of many videos and blog posts that I create as I try to figure out how the variable length flash attention function is implemented and how modern BERT's sequence packing is implemented. And I think doing those both at the same time is going to be very helpful, because on one hand, the sequence packing implementation is going to help me understand how these inputs to the flash attention interface are prepared. And then, of course, the flash attention variable length function deep dive is going to help me understand how the internals work and actually process those inputs. So that's why the video playlist on YouTube is called Understanding Sequence Packing and Flash Attention, because I'm learning those two together. All right, so that is the intro. So first, we're actually going to start with understanding how Hugging Face handles KV cache. Now, as a disclaimer, I'm not very familiar with KV cache other than knowing that it's something that saves compute time at the cost of memory. And so this was a great introduction to me as well about how KV cache works just in general. I also didn't know that Hugging Face uses KV cache by default, and I thought that was something that was needing to be implemented by the developer or the machine learning engineer or researcher, but no, it actually uses it by default. So how does it use it? So I'm using model.generate to generate my next token prediction tokens. And so I was looking at the generate source code. And I was just kind of browsing through and trying to find anything that would help me understand where this cache was created and how it was used. So along the way, I saw this prepare cache for generation function. So if I pop that open and zoom in a bit, so, where'd it go? So it takes this generation config, it takes model keyword arguments and some other parameters. And then down here, it sets in the model keyword arguments as the cache name key, it sets DynamicCache, if not requires cross attention. Otherwise, it uses the encoder decoder cache. So the model I'm using is small LM2, 135 million parameters, and it is a decoder-only architecture. It's based on the Llama architecture, so it doesn't require cross-attention, so it's going to use DynamicCache. So that's this snippet of code here. This cache name is defined somewhere up here. So if let's see, cache name, here we go. Cache name is passed key values, unless you're using hybrid cache. In that case, it's cache params. So passed key values is the name that I'm looking for as I kind of search through the code base to try to understand how this works. So that's this prepare cache for generation. And the two main things that I need to pass into it is I need the generation config and I need this model keyword arguments object. So there's a prepare generation config method. And if that opens up, let's see. Yeah, here we go. So it prepares the base generation config, and I think the main thing that I was looking at here, if I go down here, is that it returns the generation config and model keyword arguments. So I didn't really go into detail into what it does. So thankfully, that's all accessible from the model itself. So I call prepare generation config. For now, I just passed none as the keyword argument just to get something. And then I get back the generation config object, and the model keyword arguments, maybe because I passed none, is just an empty dictionary. That's fine. At least I have something to work with. So now I can pass that to prepare cache for generation. I pass those two. I pass the, I think, batch size, the maximum sequence length, and the device. So I run that. That doesn't return anything, but internally it modified my model keyword arguments. So now when I look at that, I see that here's the cache name, passed key values, and this is an object of type DynamicCache. So that was my first kind of confirmation that the default KV cache for Hugging Face, for this model, for the input arguments that I gave, is this DynamicCache object. So that was cool. That was the first kind of step that let me know that I was heading the right direction. So now that I knew that this pass key value string is what this thing is called, I kind of just searched through the modeling, the llama modeling, or modeling_llama.py file, and I was trying to look for where this is used. So inside the llama attention module, if passed key value is not none, then it calls this update method on passed key value, and then it passes to it key states, value states, layer index, and some cache arguments, and it returns back key states and value states. So if I look at the forward pass a little closer, I can see that passed key value, which is of type cache, is something that gets passed to the forward pass. So this is an object, and I'm assuming, it's somehow related to this model keyword arguments, pass key values. So, that was the next kind of confirmation of like, okay, this pass key value thing seems to be doing something with KV values, which makes sense because it is KV cache. Okay. So the next step in this kind of paper trail is to look up what this update value does. So I opened up the, oops, that doesn't seem correct. I don't know why it's opening that. I'll have to update that later. Okay, that's fine. So looking at DynamicCache.update, it has this code for updating the cache. So if key states is not none, which is our scenario, we're going to have some key hidden states to process. It goes through 3 blocks. If this condition, then it does this stuff. Otherwise, if this condition is there, it does this stuff. And otherwise, if neither of those conditions are there, it does these 2 things. And then finally, at the end, it returns that layer's key cache value and that layer's value cache value. And so this layer index is what gets passed in the forward pass of the Llama attention module. So what are these 3 conditions, and what do they say about how this is processed? So the first condition is here. If the key cache length is less than or equal to the layer index, then run through this loop and append empty tensors to the key and value cache, and then append to the key and value cache the key states and value states respectively. So what is it doing here? So there's a couple of scenarios that I was thinking through with the help of Gemini that made sense and helped me understand this. So let's look at kind of the first scenario. So let's say you're generating a response given a prompt, and the very first layer is processing the hidden states to generate the very first token. So layer state is 0, or sorry, layer index is 0, and let's say key cache is also 0 because nothing has been processed yet. Nothing has been passed through the model. This is the very first forward pass. So this is 0, that is less than or equal to 0, that's correct. Very first scenario. Okay, so let's go through this loop. Layer index is 0. This is 0. So I think this doesn't run. Let me make sure that's correct. In range 0, 0, print, let's make this I. Right, okay, so that doesn't run. So in this scenario, this loop doesn't run. We'll talk about a scenario when it does and what it means in a bit. So we go to the next lines, and it appends to the key cache, the key states for this forward pass, and it appends to the value cache, the value states. These two blocks are ignored, and then it returns those key states and value states. So very first forward pass, very first layer, we just get back the key states and value states that we gave it. So that's first forward pass. What about a situation where this for loop runs? So let's say, for example, and I'm not really aware of what situation would cause this, but that's a separate question. But let's say your very first forward pass, let's say you're starting with layer index of 2. Maybe your first 2 layers are frozen. So this is the first forward pass, so key cache is 0, or key cache is empty, so the length is 0. 0 is less than or equal to 2. So this is your third layer, layer index 2, third layer. So in this case, we are now going to have range from 0 to 2, and this is going to run for 0 and for 1, and it's going to append an empty tensor. So because we're starting by skipping the first 2 layers and we're going to the third layer, it fills them with empty lists. So it kind of pre-fills placeholders. And then it goes on and appends the key states for layer index 2, which is going to be the third value, and then the value states. So those are the 2 situations that I could think of, or I/Gemini could think of, about what happens in this first block of updating the key and value cache. So what happens here? This other condition is if not key cache layer index num_l. So num_l is going to give back the number of elements, and if not is going to run if this value is false or 0. So if we look at, let's look at torch tensor empty num_l, and that is 0. And we're going to say if not, and it does print. So if this num_l is 0, if not, we'll give a true value, and then it'll process whatever's in that block. So what would be a situation where this is the case? So let's go back to our earlier one that we just talked about. We skipped layers and we were at layer index 2. Let's say in a future forward pass, you're no longer skipping layers 0 and 1, and you've unfrozen them, and it has now some hidden states that you want to store in the KV cache. So we've already processed 3 layers, so length of key cache is 3. 3 is not less than layer index of 0 or 1, so this block would not run. What would run is this, because if you recall, we filled these skipped layer cache values, or cache kind of elements, with empty lists, and the number of elements is 0, and not 0 is true. So it's just going to assign to that layer index the key states that you pass to the forward pass. So this is basically, the combination of these two. It's preparing empty lists, and then it's filling them when you finally come across a forward pass value where you have key states and value states for those layer indexes. So kind of edge cases, in terms of, how this is used. The real workhorse seems to be this last block. So if you're not in your first forward pass, and if you're not filling skipped layers, then what do we do? So for that layer index, it concatenates any existing key states with your new key states, and it concatenates them across the second to last dimension, which we will see shortly is the sequence length dimension. And then it does the same thing for the value cache. So what this is doing is this is building the KV cache one token at a time in the case of autoregressive decoding or autoregressive language generation. One token at a time, it's building up your KV cache by concatenating the previous tensor with the current tensor across the sequence length dimension. And then finally, it returns back the concatenated tensor in this case. So yeah, that is an understanding from my perspective and Gemini's assistance of what goes on inside DynamicCache.update. And I've just, in the blog post here, this is all written out what I just talked about here. Okay, so what happens then? It returns back the key states and the value states. We have calculated the query states by passing it through the QProj layer, and then it passes those three, along with other things, to the attention interface, which actually performs the attention calculation and gives back the attention output and the attention weights. So we're kind of looking at that just in between spot of, you know, what happens right before the attention calculation is performed. All right, so I like to see things happen in real time, and I like to look at data and inspect things to understand how it's going. So that's what we're going to do. We're going to visualize this dynamic cache update. To do so, I monkey patched the dynamic cache update method, which is written up here, and I basically just copy pasted the update method from the source code, and I changed a couple things. In this first scenario, I print out this statement that says it's initializing the cache for this layer index. In this scenario here, if it runs, which it doesn't for my case, it's filling out empty cache for the given layer index. And then for this scenario, which is the most common, it's updating / concatenating the cache for the given layer index. So I had to import these guys to make the signature work. So I run that. And then I'm going to save the original dynamic cache update in this constant. And then I'm going to overwrite it with debug update. So now I'm going to have this prompt, the quick brown, and I'm going to pass that through the tokenizer, get my input IDs and attention mask, and I'm going to generate 2 new tokens. We'll talk about this parameter. It's important later. But when I run this, now I can see like how this is happening. So for the first 30 layer index kind of interactions, it is initializing the cache. Then it's concatenating for the next 30. And how does that relate back here? We had 2 new tokens. So these 30 print statements are for the first token. So that's that first forward pass where the cache is empty. And so it's initializing the cache for each of these layers. Then I already have that cache prepared for all 30 layers. So when the second token is generated, the forward pass for that token triggers the else block where I'm updating / concatenating the cache for those 30 layers. So that, you know, kind of confirms my intuition just from reading the code and talking to Gemini. And now I feel like, okay, I think I can move on. I'm sure there's a lot of detail and nuance left in terms of like how the actual update works, but maybe not, right? Like I think it's just appending to this cache. Cache has a length, and everything else is, you know, PyTorch top operations. So I don't think it's more complex than that, but you know, famous last words. All right, cool. Now I'm going to reassign the original update version because I don't want to see these printouts everywhere else. Okay, so that is, you know, understanding the visualizing the dynamic cache update. Now I'm going to go back to the past key values, so the cache itself, and I want to inspect the contents of the key cache and the value cache during model.generate. So I'm going to reload my tokenizer and model. I don't know why it prints this out. Here's my prompt, the quick brown, and we're going to expect it to say Fox. Here are my input IDs. There's 3 tokens in my prompt. And then here is this return dict in generate equals true. And I'm going to pass that so that it gives me back this generate decoder only output object. And most importantly, it gives me back the past key values so I can access the key and value, the KV cache. So I'm going to run this. I'm going to decode the outputs, and just to make sure, like, yeah, this makes sense. The quick brown fox jumps over the lazy dog. And if we look at the number of tokens in the sequence, final sequence, we have 8. That's because we had 3 from the original prompt, and then I had max new tokens defined as 5. 3 plus 5 is 8. That makes sense. All right, let's take a closer look now at the actual KV cache. So both of them have 30 elements, which makes sense because we have 30 layers in the model. It has this scene tokens parameter, which the warning here said that it was going to change to, I think, cache position, I think was what that's going to change to. And this is 7, which makes sense because the very last token, the 8th token, will have seen 7 tokens before. That makes sense. And now, for the fun part, we can actually iterate through the key cache because it's some like list-like object, and we can print the value of our key states for each layer. And we can see that they are all shaped the same. This is one batch item, so batch size of 1. There are 3 KV heads, which will prove or confirm later on. The sequence length is 7, and the hidden dimension for each head is 64. So that's how we're going to interpret these. So if you recall, in the DynamicCache update, it was concatenating across dimension equals -2. So here's -1, here's -2. This is the sequence length. Great. Looking at some config values, the number of attention heads is 9. The number of hidden layers 30. The number of key value heads is 3, and that confirms this value here. If we look at the first layer's self-attention's kproj out features, we see that is 192, which is 3 times 64. So that checks out. And the value cache is similarly structured. So same shapes as the key cache. And just as a sanity check, or just confirmation of a basic idea, I store the initial key state, and then I iterate through the key cache, and I'm seeing if the initial key state is equal to all the other key states. And it's not, which makes sense because all of our different layers in our models have different kproj and vproj weights, and they're all learned weights, and so they're all different. So the hidden states for the key and value are not going to be equal. It's just their shapes that are equal. Okay, great. So what does that do? That gives me an insight into, number 1, what past key values looks like, right? It's part of this decoder, generate decoder only output object. Number 2, I can very easily access the key cache and the value cache. I can iterate through them, and then I can access the key and value states. So that gives me some practice on how to use these things. So we're kind of slowly building up familiarity with each of these kind of APIs, I guess, or each of these objects, and doing more interesting, complex things. So now that I have understood what these key values or key states and value states look like at the end of generation, I now want to see what they look like at every step of the autoregressive generation process. So what I'm doing is I'm going to create a hook, and I'm going to pass that hook to the register forward hook function or method. So just to clarify and correct myself, I had a previous video and a blog post where I incorrectly said that you can't use register forward hook for the Llama attention module because it doesn't capture keyword arguments. And by default, that is true if you look at the documentation for register forward hook. If with keyword args is false or not specified, the input, which is, where's the input? I think it's the input to the hook, contains only the positional arguments given to the module, or the args. There we go. That's the input. Keyword arguments won't be passed to the hooks and only to the forward. The hook can modify the output. It can modify the input in place, blah, blah, blah. If with keyword args is true, the forward hook will be passed the keyword args given to the forward function and be expected to return the output possibly modified. The hook should have the following signature. So module args, keyword args. So this keyword args is what we're interested in. The reason being that if we look at the Llama decoder layer and we see how the self-attention module's forward pass is called, we can see that there are no positional arguments, even though it's a little confusing. There's keyword args down here. But straight from the start, hidden states equals hidden states, attention mask equals attention mask, etc. So there are no positional arguments in this forward pass. So what we have to do here is that when we register our hook, we just pass this with keyword args equals true. So what am I using here? I have this wrapper create hook function, and the reason I have that is because I want to view the count of how many times this forward pass is called. And basically I want to see which is the number of token that's being processed out of the 7 tokens that are going to be processed, or I guess 5 tokens. So I define a count here, then I define the hook function with this signature that they specified in the documentation. I reference the non-local count, and then I print out the count, and then the shape of the first value in the key cache. My previous experiment where I was printing out the final key cache values or shapes, I saw that every layer had the same shape. And so, at least for now, for the first version of this, I'm just printing out the first one just so I don't get a wall of text. Then I increment the count, and then I return the hook function. So I'm getting my hook function here. I'm getting my attention layer here. On the attention layer, I'm registering my hook, and that's all I have to do. So now when I call model.generate and I use a max new tokens of 5, I can now see as each token is being processed, I can see what the shape is of the first layer's key states tensor. Or in other words, I can see what the shape is of the first object in the key cache. And this is very cool because now you can actually see the auto-regressive nature of the model happening live, right? You can see that first token, there are 3 previous tokens that have key vectors. The second token has the 3 prompt tokens plus the first token. The third one has 3 plus 2 is 5, 6, 7, right? So you can see how the next token prediction is unfolding from the perspective of the key cache. All right, so that was kind of iteration 1. Now what I want to do is I want to look at the first 5 key states in my key cache. So what that means is I want to look at what is the key cache item for the first 5 layers in my model. And then I'm going to print that shape, and then I'm going to print the count before that so it's a little easier to see. I'm doing hook handle.remove each time so I can run separate cells and I don't have to worry about that. So I run this, and this is really interesting to see, right? So why is there just 1 value here, and then why is there 5 values here, And then why is the first one always one more than the other four? You know, these were initially when I printed this out, I didn't print it out this way. I printed it all as a single column of text, and it was confusing me, and it actually confused Gemini as well. But then I eventually figured out that, okay, what's happening is that when the first token is being processed, this is the first forward pass, and the first forward pass has an empty key cache, right? Because in that first forward cache, if you remember the first if block in the DynamicCache update method, the first forward pass is instantiating the first layer's key cache. So that's what we're seeing here. We're seeing that when you process the first token, the only layer that has a key cache item is layer index 0. And for layer index 0, it sees the previous 3 tokens, which are the prompt tokens. Nothing else exists yet. Cool. That happens, that forward pass across all layers happens. Then we move on to the second token being generated. And here we can see that for layer index 0, so the very first layer, it has now seen 4 tokens, the 3 prompt tokens plus the first token that was generated. These 4 are the key states for layers and layer indexes 1, 2, and 3, and 4, right? 1, 2, 3, 4. So 0, 1, 2, 3, 4. Those have not yet seen the new token. And so they are still containing the key states from the first forward pass that generated the first token. And the reason is, if you look at where we're getting this attention layer from, we are only looking at the first layer, so layer index 0, and we're registering our forward hook only in that first layer. So from the first layer's perspective, in this second iteration of updating key cache, it has updated, but these other ones haven't, because we haven't gotten to the forward pass of layer index 1, 2, 3, 4, 5, etc., all the way up to 29. And we see that pattern repeating. When the third token is being, or has been processed by the layer index ID of 0, it has now processed 5 tokens, or it has now seen 5 tokens, and it's generating this 6th token. But the other ones have not seen this the new token yet. And then we go on to the 4th token being processed, and we see that this has seen the past 6 tokens. These layers have not yet encountered the new token in the forward pass. So in this way, from the perspective of layer index 0, the other subsequent layers cache tensors are 1 token behind, since the new token's hidden states have not passed through the model yet. So this was something that tripped me up when I was looking at these printouts. So hopefully printing it out this way, you can kind of visualize it. So again, just to review for my sake, the first forward pass, the first token that's being generated can see the past 3 tokens, which is the prompt. The second forward pass can see the prompt plus the first token. The third forward pass can see the prompt tokens plus the first 2 forward passes, and so on and so forth. Till we get to the 5th token, it can see the prompt, 3 tokens in the prompt, plus the 4 previous tokens that were generated, and it'll generate the 8th token. So it can see the 7 previous tokens. So I think that now makes sense. Okay, let's see what we have here. This is kind of just expanding upon what we're looking at. This is actually eventually going to tie back to the flash attention variable length func docstring, which I promise we will get to. This was a bit of a detour, but I think it was necessary to kind of understand these things. Plus, I had never seen how KV cache works, so this was really cool to see. So what I want to do is I want to copy the llama attention forward pass, how it handles the query states. So look at how that happens here. Let's go to llama. Let's see, where's llama attention? Llama attention forward. The input shape is all up to the second to last hidden states dimensions, and then the hidden shape is the input shapes -1, and then the self hidden dimension, and then the query states is you passing those hidden states through the QProj layer, changing the kind of reshaping it with view, or kind of reorganizing it with view, and then transposing it so that it's set up correctly for the attention calculation. So I'm basically just copying these 3 lines of code and dumping them in here because I know that I'm getting the same arguments and keyword arguments that the Llama attention module is. So I get my query states, and then basically I just print out everything. So I print out what is the length of the key cache, what is the shape of the query states, the shape of the first key state, and the shape of the first value states for layer index 0. All right, so we run that and we see what we expected. So the first token that's being generated, the KV cache hasn't been built yet, so it only has 1 item, which is the layer index 0. Second token has all 30 built, so it has 30 items, and then that stays consistent throughout the process. Query states, the first set of query tokens are the prompt tokens, so that's why we see a 3 here. And then for each subsequent next token being predicted, we have 1 token at a time, so we have query states for just a sequence length of 1. And this is the number of attention heads, 9. The key states start out by looking back at the prompt tokens, and then for every subsequent forward pass through the model, we have 1 more token that we can see, and the 8th token can look back and see the 7 previous tokens. And the same thing, same pattern, 3, 4, 5, 6, 7 for the value states and the value cache. So just a nice little recap to understand, how this functions as we generate 1 token at a time. Something that we will see later in the flash attention varlen func docstring is that this is an example of a situation where the query states has a different sequence length, right, 1, than the key and value states, specifically the key states. So we have 4 key tokens or 4 key vectors, but we only have 1 query vector. So this is going to be perfect as a concrete example of the docstring example of the causal mask, where we had a different number of sequence lengths for the query and the key. Okay, I think that's everything I wanted to do for that. All right, the last thing, so while we're here, I want to understand which flash attention interface is being used currently by model.generate. So I have flash attention installed, so it should be using that, because when I loaded the model, the attention implementation, I said use flash attention too. So there are 3 functions that are being used by model.generate. And the way I know that these are used is because I've done this exercise before when I was trying to understand what exactly in the input to the model triggered the use of flash attention varlen func. And there are a couple things that trigger it. One thing that triggers it is if your position IDs restart at 0 at any point, then that triggers the varlen func usage. And the second thing is if your attention mask is not none, then that triggers the flash attention varlen func usage. So those were 2 things that I knew from the previous exercise, but I also double checked that because I had kind of forgotten what I had done. So I import get source from inspect, and I look at the forward pass of the self attention module. And there's a lot of stuff in here, but what I'm really interested about is this block here. So if the attention implementation is not eager, which in our case it isn't, is it SDPA? No, it's not. So otherwise, attention interface is in pulling out the whatever all attention functions value is for the self-config attention implementation key, and then that attention interface is being called and being passed our query, key, and value states, and so on. So what I did is I imported the all attention functions constant, and if I look at my model.config underscore attention underscore implementation, it's flash attention 2. And if I pass that to all attention functions, the flash attention interface, or the attention interface, is flash attention forward, and that lives in transformers integrations flash attention.py. So that's how I identified and kind of confirmed, which flash attention interface wrapper is being used. And then once you look in that one, you can see that, so that's my Llama attention forward. You can see flash attention forward, and if you look at flash attention forward, you can see that underscore flash attention forward is used. So there's 3 forward methods that I have to, well, 1 forward method and 2 functions, utility functions, that I have to monkey patch in order to kind of debug and understand what's being called when. So that's what I do down here. I just wholesale copy paste the underscore flash attention forward method, and in there I'm just putting in some print statements. So if attention mask is not none, flash attention varlen func is being used. So here's attention mask is not none. Here's the varlen func. If position IDs is not none, and it's really this torch diff of position IDs is greater than 0. So basically, and not torch diff is greater than 0. So if you have position IDs, actually, does it give an example? How do I pull that out again? I don't know. But if position IDs goes like 0, 1, 2, 3, 0, then the difference between 3 and 0 is going to be -3. And that is not going to be greater than 0. So this is going to be false, and not false is true. So that's one of the conditions that you need to pass. So if that's the case, then I want to print out that position IDs is not none, and so flash attention varlen func is used. And then finally, if everything else, none of these work, or none of these are triggered, then the non-variable length flash attention func is used. And so I'm just printing that out. So nothing fancy, just putting some print statements in there. All right, the next one is this flash attention forward, which is kind of one level higher. And here I'm just printing this line where it says calling flash attention forward, and then I'm replacing underscore flash attention forward with my debug flash attention forward. So that is run there. Let's make sure this was run. And the final one that we have to modify is the forward pass for the self-attention module. And what we're doing in here is I'm commenting out this all attention functions object indexing, and instead I'm just hard coding my debug flash attention forward as the attention interface, and then that is the attention interface that's being called. So this is ensuring that it's using my debug version. All right, so let's load up the model again. And I want to bind my function as a objects method. So I'm going to use this types.method type. I think you can also use the dunder-get method for that. There's a blog post I had about, I think it's called the descriptor documentation. But yeah, anyways, what we want to do here is we want to grab our attention module. I'm going to save the original one, even though I don't really use it later. And then I'm going to say, I want to bind this function as a method for this object. So that's something that is very nifty and very useful. And so now when I put my forward hook and forward pass is called on self-attention, it will trigger all of my debug functions that I had because they are now methods. Well, to be precise, debug forward is now a method for this attention layer instance. And then the other 2 utility functions are called from inside there. So now if we run this, same hook function process as before, and now I can see flash attention forward is called, flash attention func is being used. And then here's the printout of everything we saw before. So this confirms that the non-variable length interface is being used. That makes sense because I only have one item in the batch, so there is no variable length. Everything is just one prompt, one sequence length, one token at a time. Very straightforward. Okay, so quick recap of what we've learned so far. HuggingFace's model.generate uses KV cache by default, and it's called DynamicCache, and it's stored as past key values. For most scenarios, the dynamic cache is updated by concatenating the previous tokens, key cache and value cache, with the key states and value states generated by the new token being processed. As the next token is generated for the given prompt, query states has a sequence length of 1, whereas key cache and value cache tensors sequence dimension increases by 1. This directly relates to the flash attention varlen func causal mask docstring example, which we'll look at again in a second. And then finally, model.generate utilized the flash attention func interface for my scenario. So if we look back at this snippet again, here we had a query vector or query length, sequence length of 2, key sequence length of 5. So we have this 2 by 5 matrix for the causal mask. And then we have it flipped here, sequence length of 5 for our query, sequence length of 2 for our key. We have a 5 by 2. So if we go back to the beginning, I was reading this docstring as my very first step of my very first phase of understanding flash attention varlen func. And I didn't understand what this was because I've never dealt with it. And through my conversation with Gemini, we discovered that KV cache would be an interesting way to see this while we're at it. So that's kind of a long-winded way of kind of getting to this thing eventually. So let's actually try to understand what's going on here and why, now that we've seen a concrete example where the sequence length for the query is different than the sequence length for the key. Now, just a clarification, this is for attention varlen func, but flash attention func also had the same docstring example, so I think it's implemented in the same way. All right, so let's annotate these causal mask examples, and let me zoom in a bit. So we have query 0, query 1. We have key 0, key 1, key 2, key 3, key 4. So 5 key tokens, 2 query tokens. Here, for query token 0, it attends to everything but the last key token. Query token 1 attends to all key tokens. And this is a key piece. The final query token sees all 5 key tokens. The first query token sees only the first 4, and we'll get to why. Let's annotate our other example. We have 5 query tokens, 0, 1, 2, 3, 4, and we have 2 key tokens, 0, 1. And here we have a lot more things masked out. So key token 0 is only attended to by queries 3 and 4. Key token 1 is only attended to by query 4. So again, the final query token sees all tokens, all key tokens. And then as a consequence, because there's only 2 key tokens to look at, the first 3 query tokens do not see any tokens. And we'll see another way of looking at that in a second. So another way to think about this is that we are offsetting the shorter sequence in both cases. And the way we're offsetting it is, I think it's subjective. I could be wrong. Maybe there's only one way to do it, and this is the way. But you have 2 sequences that are different in terms of their lengths. So you have to pick, how are we going to align it? And what they've set up here is the causal mask is aligned to the bottom right corner of the attention matrix. So they're telling us how they're choosing to align these 2 unequal sequences. And the way they're choosing to align them is that the last token of each sequence attends to each other. So the last query token attends to the last key token, and everything is reverse engineered back from that, which we'll see in a second. Same thing here. The last query token is attending the last key token, and everything else is kind of reverse engineered back from that. Okay, so looking at a couple of visuals, the last tokens in each sequence are aligned because this Q sequence is shorter, we have these offset positions because we have to make up this difference of 3 more key tokens. And in this case, all the offset positions have 1s because there are more key tokens to look back at than query tokens. So causality tells us that we can look at the current token and all the previous tokens. So if we're aligning this last token, Q1 and K4, we can look at the current token, which is K4, and all previous tokens, K3, K2, K1, K0. If we look at Q0, we can look at the current token, which is K3, K2, K1, K0. So even though these are kind of, filler positions, there's nothing wrong in looking back. And so we can look back at all 3 key tokens. On the flip side, when we have more query tokens than key tokens, the offset positions are masked out because there's not enough key tokens to look back at, right? Everything happens one sequence at a time. When we looked at our model.generate QKV shapes, we saw that Q was always a sequence length of 1 because it's next token prediction, right? Autoregressive, 1 token at a time. The key states had an increasing sequence length. So it went 3, 4, 5, 6, 7. So every next token you're like building up 1 more key token at a time. So if you have only 2 tokens to attend to, and you're starting by attending the last query token to the last key token, there's only 2 query tokens that are going to attend to the key tokens. The first 3 are not going to attend to anything because there's not enough key tokens to look back at. So that was kind of my visualizing and conceptualizing how this worked. And this just kind of explains. I also added this kind of more mathy way to look at it. And it's a bit long, so I'll just cover kind of the main points that I understood. So causality in language modeling means that you can only see the current and previous tokens keys. So if you have different sequence lengths, you have to pick how the Q and K tokens are aligned. And in the case of the variable length flash attention function, they choose to align Q and K such that the last token in Q is aligned with the last token in K. So Gemini had this concept of present moment. So what is our present moment? It's this final Q token attending to final K. So if we look at here, our present moment is Q4 and K1. Here, our present moment is Q1 and K4. Everything that happens in the past is to the left, right? Everything happens to the past is up. And there's not enough tokens for these 3 queries to attend to in the past. That's why they're zeros. Okay, that's kind of like step 1. So we're going to say that I is the position of the query tokens and J is the position of key tokens. When we have misaligned, or I shouldn't say misaligned, when we have different sequence lengths, causality is defined as J less than or equal to I plus this offset. If we go back up here, if we had a square matrix, it would just be J is less than or equal to I. But now because we have a rectangular matrix, we have to take into account this offset. So first what I'm going to do is I'm going to walk through a concrete example of this equation, and then I'm going to show how we can derive this equation using the definition of present moment and I, the position of query tokens, and J, the position of key tokens. So this is our first causal mask where we have this one here where we have 5 K tokens and 2 Q tokens. So we go from 0, 1, 2, 3, 4 for all of our first query tokens, or for the first query token of 0. And then J, again, goes from 0, 1, 2, 3, 4, where I is 1, which is our second query token. So we're just going to plug in these values here. So I is J less than or equal to I plus sequence length K minus sequence length Q. Sequence length K is 5. Sequence length Q is 2. So 5 minus 2 is 3. So is J less than or equal to I plus 3? So when J is 0 and I is 0, 0 is less than 3, true, right? 1 is less than 3, 2 is less than 3, 3 is less than 3, 4 is not less than 3, so this is false. So if we go back up here, 4 is not less than 3, so this value is 0. So this equation so far matches our intuition. Then when we look at the second query token, we have 0 less than 4, because now I is 1, so 1 plus 3 is 4, and all 5 of our key positions are less than or equal to 4. So all of these are true. We go back up here, all of these are 1s. Cool, that matches. All right, so where does this j is less than I plus sequence length k minus sequence length q come from? So we're going to define a couple more things. We're going to say qi is a query that is sequence length q minus 1 minus I steps before the end of the query sequence. So this minus 1 is because Python starts at 0. Kj is a key that is sequence length k minus 1 minus j steps before the end of the key sequence. So if we look at our examples where we have 5 keys and 2 queries, query 0, sequence length is 2, minus 1 minus 0 is 1. So it's 1 step before the end. All right, so that's where this little equation kicks in. Our second query, query 1, is sequence length 2 minus 1 minus I 1. 2 minus 2 is 0. So 0 steps before the end, it is the end. For k, we get the same thing, except sequence length of k is 5. So 5 minus 1 is 4. So we get 4 minus 0 is 4 steps, right? So 1, 2, 3, 4. What is this? 5 minus 2 is 3. Hold on, I just confused myself. Sequence length is 5, minus 1 is 4, minus j equals 1 is 3. So here we go, 3 steps, 1, 2, 3. K2 is 2 steps before the end. K3 is 1 step before the end. K4 is 0 steps. So this is all going back to that comment they had in the docstring that the causal mask is aligned to the bottom right corner of the attention matrix. So we're our present moment, as Gemini called it, our present moment is this last token. So we're kind of just defining distance of other tokens from this last token, this bottom right corner. Okay, cool. So we're picking a present moment. We're calling that P, the last token in each sequence. And so we're going to say that we have from this last token, Pj has to be less than or equal to Pi for causality to exist. Kj, our keys, has a position on the timeline, present moment minus the number of steps that j is from the end, which is this sequence length k minus 1 minus j. Qi has a position on the timeline, Pi, which is our present moment, our last token, minus the number of steps away from the end. And so causality requires that we can only look back, right? Pj has to be less than or equal to Pi on this like unified timeline. So Pj is less than or equal to Pi. We plug in our Pj and Pi values. The P's cancel out. And then I'm distributing the minus sign into these guys here. So we get minus sequence length k. Minus a minus is plus. Minus a minus is plus. Minus sequence length q. Minus a minus is plus. Minus a minus is plus. Great, that works. Now we want to isolate this j on the left-hand side. So I'm going to add my sequence length k. I'm going to subtract this 1, and that will leave me with j. These 1s cancel out, and I'm going to reorder this. So I have j less than or equal to I plus sequence length k minus sequence length q. So this sequence length k minus q is our offset between the two sequences, and this has to be true for causality to be true. So that is kind of the more math-oriented derivation or explanation of this whole bottom right attention matrix fixation that we have. And then I go through the same steps for the second causal mask and just kind of show that, yeah, this matches with the 0s and 1s that we have. Okay, so that is it for this exercise. You know, I think I don't know if I underestimated how much time it's going to take to understand the variable length function, but I certainly did not think that I would get hung up so much on the docstring, but that's fine. I learned a lot. This was the first time I've actually understood KV cache, and it's really cool to see that it's a default implementation in Hugging Face. So that was really cool to see. As I said, I'm also working on a modern BERT sequence packing implementation walkthrough, and so there will be many such deep dives for that, many such deep dives for this flash attention understanding, and so I think combining those two should give me a nice back and forth for kind of what goes into flash attention, and then what happens inside flash attention, and then what gets returned back. So just going through the key things that I've learned. Model.generate uses KV cache by default. It's called DynamicCache, and it's stored as past key values. In most cases, unless it's the very first forward pass or you skipped some layers, DynamicCache is updated by concatenating the previous token's states with the current token states for key and value, respectively. As the next token is generated for a given prompt, query states has a sequence length of 1. In the first forward pass, it's 3 because it's processing the prompt. Whereas key cache and value cache states tensors, sequence dimension increases by 1 because now we're looking back at one more token every time. So this directly relates to the flash attention varlen func causal mask docstring example where the Q and K sequence lengths are different. Model.generate utilized the flash attention func interface, so the non-variable length one, because we did not have variable lengths. We had one item in our batch. The causal mask for flash attention variable length is aligned to the bottom right of the attention matrix, and what that means is that the last tokens of the Q and K sequence are aligned. Causality, when Qi and Kj sequences are of different length, is satisfied by this equation: j is less than I plus the offset between the two. When there are more query tokens than key tokens, the offset results in zeros in the mask, as there are not enough key tokens to look back at by all of the query tokens. But when there are more key tokens than query tokens, the offset results in ones, as the query tokens can look back at more key tokens. And this last instance is, for example, we see an instance of that in our model.generate example, where we always had one query token, the one that's currently being processed, other than the first prompt processing. And we always had more key tokens, right? We had 3, 4, 5, 6, 7. And so our current token can always look back at all of the previous key tokens, no matter how many there are, up to the maximum, sequence length of our model. So that's it for this video. This will be posted in a blog post version shortly, so all the code will be in there. Thank you for watching. Please like, comment, subscribe, and I will see you next time.